Hey everybody. So today I'm going to be talking about encoders and decoders within hyperdimensional computing, which is the main difference between hyperdimensional computing and transformers. As to why exactly you would want to utilize hyperdimensional computing, this difference is why. And it's a very simplistic difference to explain, and it's a very simplistic difference mathematically. But this difference makes all the difference in the world. And the main difference is that transformers are probabilistic encodings and deterministic decoding, whereas hyperdimensional computing is deterministic encoding and probabilistic decoding. And we'll get into this within this lecture by focusing primarily on the encoding mechanism and explaining this out. The bottom line to get into within this is that there's no escape of linear algebra, geometry, and calculus within this equation, right? And I say this over and over again in a lot of different lectures and in a lot of different areas. What we're going to dive into very specifically deals with this transformation between linear algebra and geometry. That's what we're dealing with, and that's what the bottom line is of these models. It's not computer science, it's not computation, it's mathematics. And then so diving into this and giving you a simple illustration of this up front, looking at a standard word vectorization and how it works. If we take a sentence, the cat sat in the mat, the actual vectorization, transforming this sentence into its kind of like mathematical equation, is almost kind of like virtually the same in a lot of it looks the same between standard word vectorization and hyperdimensional computing. So in this instance, with standard word vectorization, we have the cat sat on the mat, and then it breaks it down into arrays. And then these are the full arrays that we're looking at here, right? And then so we have the full array that breaks down from this sentence utilizing word vectorization for the actual encoding process. And then we get an encoding that we can, an embedding that we can embed into a model, which can then be fine-tuned and decoded. This goes into the biggest fundamental difference between standard word vectorizations and transformers and hyperdimensional computing and this hypervector encoding is that with hypervector encoding, there's no backpropagation, no gradient descent. You're not fine-tuning the model is the bottom line, right? And we'll dive deeper and deeper into this concept, but I want to introduce that concept to you now up front and over again as we go through this, that with this encoding process, the main difference is that when it comes to decoding time, we're never fine-tuning. No gradient descent, no backwards propagation, none of that. How do we get around that? Let's dive deeper into this. So when we look to the hypervector encoding, we take this same sentence, the cat sat on the mat, and then what we're doing is we're creating arrays, and same thing as we did before with the vectors, except for we are creating multi-dimensional arrays. So in this instance, I'm creating a 10,000 dimensional array, and the 10,000 dimensions are set. Some of these arrays will be set to 0 up front, right? Initially, the model won't have 10,000 dimensions on cat. For example. But so a lot of them could be 0, but I set the dimensions up front to 10,000. So set standard 10,000 dimensions. And then we go through, and then this process utilizes essentially a process called binding and bundling. And then that's entirely what we're doing. And then to shape in your mind what binding and bundling is in simplistic terms is very simplistically, we are binding the words together. So like sat, cat, the, on, mat, and we are bundling them into the full sentence. So sat, cat, the, on, mat, and then binding and bundling. And then within hyperdimensional computing, we do this via linear algebra. And very simplistically, we do this via linear multiplication. And then so one of the benefits of hyperdimensional computing is that this mathematical process, this embedding process, is very simplistic mathematically, as opposed to the transformers process of embedding, which is not a linear process. It is a probabilistic process, which is far more computationally expensive. And then it introduces that probabilistic aspect from the beginning. Both of these models have probabilistic aspects within them. So the fact that hypervectors and HDC utilizes linear algebra up front and then probabilistic encoding, decoding, as opposed to probabilistic encoding and linear decoding isn't really an advantage to me one way or the other, because they both introduce the same concepts. One at the beginning, one at the end. That's my engineer mind though, right? So to me, there's not a difference in this process between introducing one in the beginning and one at the end. You're introducing the same thing, but that's why I'm an engineer, right? My brain thinks more simplistically in these terms, just breaking it down to you how I think of this. So essentially, when we break this down mathematically and we look at these representations and we compare, in this instance, we're looking at word-to-vec vectorization as opposed to hyperdimensional computing. With word-to-vec vectorization, it represents words as dense, low-dimensional vectors. So that whole entire array, that whole entire mathematical equation ends up being between 100 and 300 dimensions, whereas with hyperdimensional computing, it's 10,000 dimensions, or we can set it even higher, right? We can set it to 100,000, a million dimensions. And then again, some of those will be 0 up front. And then what a dimension is, clearly to you, if you haven't seen earlier in this and just reiterating it, is attributes of a cat, right? So attributes, dimensions of cat in this instance would be feline, hunts mice, nocturnal, predator, cute, fluffy, etc., right? Everything that could be associated with cat, and in this instance, 10,000 associations with cat. And then I can encode those in the model, and then it creates a dictionary. That's exactly, if you are thinking along those lines, that's exactly what we're doing, right? Is we're creating a dictionary of attributes for the model to follow. And then so essentially within this encoding process, the biggest takeaway within this is that, again, we don't do no fine tuning and no back propagation. So how do we get this information then into an HDC model as opposed to like a transformers model? And the bottom line is think of this like rag tuning as opposed to fine tuning a model overall, or training a model overall. So you take your entire corpus, your entire data set. Let's say that your entire data set is a 25-page PDF. Then we upload and we create hypervectors for that 25-page PDF, and then every single hypervector that is created within this network is based off of the entirety of the data, right? So when you add data, you're reshaping this. It's the shape of this changes every single time that you add data. So like you're rag tuning essentially every single time that you add data, but you never fine tune. And then that shape of that end result shape and that changing of the shape of the data as you load more data in becomes the structure of the model itself. And then so again, no back propagation, no gradient descent. You're not training it on that data as it goes through with that encoding process. And then so like the difference here comes in with that decoder, right? Which is why we're focusing this lecture just purely on the encoding mechanism. So if you're wondering how exactly does that translate differently on decoding, that's where we'll get into that element. But very specifically, what you need to know and understand from here and from this particular lecture with regards towards the encoding process is that, again, transformers is probabilistic encoding and deterministic decoding, utilizing calculus and geometry for the encoding mechanisms, and then linear algebra for the decoding, whereas HDC is deterministic encoding and probabilistic decoding, utilizing linear algebra for the encoding, and then geometry and calculus for the decoding. So the exact opposite. And then in the next lecture, we'll dive deeper into that decoding process. So look forward to seeing you in the next lecture.